Yeah. Yeah. All right.
So, when you said that you were watching some Jack Weston videos, what topics were you covering in the Jack Weston?
I was trying to cover the same ones. So the kinematics and dynamics. So definitely couldn't get through it, but we talked about force and the derived units, like like chapter one of physics. And then I
Mhm.
skipped down all the way to the one that talked about like working energy, but I couldn't watch it. I just decided to read the book for working energy.
Okay. So why don't you
And
tell me a little bit about force?
okay.
What is force and how do we calculate
Oh. Off the top of my head, or can I use my notes?
it? Let's start by trying from the top of our head.
Or my notes. Um, there's like three Newton laws when it comes to force. Force is just that I don't know like the definition, but I know that it's F equals ma, but the
Okay.
units matter and can be derived. Um, like it can be derived to energy and forgetting the other one. But the units is newtons equals kilograms times meters over second squared. And I'm remembering that energy is joules and it's kilograms times um meters squared over second squared. And the other one that I can't remember the name right now is kilograms meters squared over seconds cubed. Can't remember what it is, so I don't know what the equal to unit is. But yes, I knew that they were derived. Force. Yeah, that's what I got for force.
Okay. Okay, so mass times acceleration makes our force. Excellent. You got the units down. That is exactly what you want. I think that what you were thinking of with um so the units
Or
for energy.
power.
You got, yes, power is the one after that. Power is energy per second, if I
Yes,
remember
yes. Dark
right.
cubed.
Okay. Okay, nice. So with with force, you said it's mass times acceleration. So if that means that in order to calculate a force, we need to have an object that is moving, right?
Mhm.
Literally, that's all that is. Force is just the describing the movement of an object, not just velocity. It's how much that velocity is changing over time, acceleration. So the idea behind this is that um, whenever you see a question that brings up a moving object, they could ask you about force. But force equals mass times acceleration. So that removes a little bit of the stress from that. Then they could ask about energy, but you know that energy is just force times what? You knew what the units were. So can you tell me what the equation for energy is?
Oh, force times distance.
Force times distance. Excellent. That's
My
basically
connection is
just,
unstable.
oh, that's okay. All right. Can you hear me okay?
Hmm?
Okay. Yeah. So energy equals force times distance, right? So we usually call that work. What I think about with work is basically just the energy needed to do something. Um,
Okay.
Now,
Okay,
power, we
because
talked
I
about
put
being at
energy.
power, we talked about energy over time. So,
Yeah,
what
I always forget
we,
that.
yeah, it can be a little bit, it can be a lot. The unit for power. Do you remember what the unit for power is?
Watts.
Watts. Exactly.
Okay. Yeah, yeah, yeah. Power should be in watts. What, like batteries and stuff like that? Yeah.
All right. So you said something about Newton's laws. And then you started talking about the definition of force, which is awesome. What is Newton's first law?
All energy is the same, like equal and is the same.
So
It's not like
it's
created
not
or
quite
destroyed.
talking about the energy. That is referring to laws of thermodynamics, which are also
Mm,
pretty high yield.
mm.
So Newton's first law, think about it, and remember, Newton is talking about force, not necessarily energy. So, and force, remember, is describing mass times an acceleration. Acceleration being a change in movement. So force has to do with motion, right? Newton's first law has to do with an object. If I have something and I just like I'm out in a vacuum of space and I throw a ball, is that ball ever going to stop?
Yeah. I mean, in a
What's
vacuum,
in a vacuum?
that means like it's like sucking the ball
Not
into like
quite.
a,
So remember that a vacuum just means that there is no matter. So like a vacuum cleaner isn't an actual vacuum, but they call it a vacuum because what vacuums do, because they have no matter in them. Uh, do you know? Are you familiar with the process of diffusion?
yes, yes.
Okay, awesome.
And like
So
how it just moves.
yeah,
Oh, how
so
it's like simple.
pretty much yeah. So diffusion is the idea that if I have a lot of stuff over here and not a lot of stuff over here, the stuff over here will move, right? Until it balances.
Mhm.
So because of that, with in a vacuum, when you have little mass, like almost no mass there, no matter, nothing, there's an empty space, and the anything that has matter will try to move to fill that space. That's why we call a vacuum cleaner because we're like creating that suction effect by making a decrease in the matter in that area that's bringing more matter into it. This is also how an airplane flies, but we'll talk about that in a bit. Um, Newton's first law is talking about if I'm in a vacuum and there's no matter, meaning that there's nothing in that area at all. And I don't have any, like if let's say that I also don't have any gravity. If I
Mhm.
throw a ball, what is going to stop the ball from continuing to move forward?
Nothing.
Exactly. When I throw a ball on Earth, what stops it from moving forward forever?
The gravitational.
Yeah, gravity. So just a conceptual point. If I'm on, let's say that I'm on like I'm on Earth, but I I'm in an anti-gravity place, somewhere where there's no gravity at all, and I throw a ball. Still on Earth, but no gravity. Is there anything that will stop it?
Yes.
What?
Now that goes into force. Um, I feel like it was, I don't want to say air, something about the air.
Something
It
about
was
the air. Okay. So what is air made out of?
mm,
What do you mean? I don't know.
oxygen. You know what? Air that we breathe. We
Yeah.
breathe in oxygen. So,
Oxygen. Okay, sweet. Yeah. So we breathe in oxygen. The air contains oxygen and it's got like nitrogen and like carbon dioxide and all kinds of stuff, but a lot of it's like oxygen and nitrogen. But the point is, those are molecules, right?
mhm.
Physical pieces of matter that are sitting there in the air. When I throw a ball against that, that ball is slapping against all of those molecules.
Friction. No.
Yes, it's
Okay, so
creating a
it is
type of
friction
friction.
force that allows it to fall down.
Not down. It's the friction force that's well, yes, but it's the friction force that slows it down from going horizontal, and while it's going down, it also slows it down in its ascent. Basically, anytime the ball is in contact with those particles, they're slowing it down.
Okay.
When it's in a fluid like air, we don't call it friction, we call it drag.
Oh, okay. Yeah, that's why I was like, it's not friction. It's something with the air.
But conceptually, it is friction.
Okay. Okay.
So Newton's first law is that if an object that is in motion will stay in motion unless influenced by an outside force.
Okay.
So if I have a ball and I just set it in a vacuum with no gravity, just this isolated place in space, and I just like hold it right here and then just let go and leave it there. No force applied to it, nothing. Is it ever going to move?
Why do I feel like it's not going to fall, but like it will just stay in like that area, kind of like just not still. I
It,
don't
it,
know.
so you're thinking that it's just gonna kind of like
Yeah. No, it'll just stay in that area or just stay.
I think I see what you're saying. So the idea is that it's going to just stay motionless. Any
Okay.
object that is not being acted on by any force is not
Mhm.
going to move because Newton's first law describes this. So an object in motion stays in motion, but an object at rest will stay at rest unless acted on by an outside force. Like look at the desk or the table that you're sitting at. You have any number of things that could be on top of it. For example, I have a water bottle right here. If I set my water bottle on the table, it will stay there for eternity unless an earthquake comes and shakes it or somebody comes and picks it up. Because no outside force is acting on it outside of the gravity, but gravity isn't going to suck it down further. Um, but it's not being acted on by an outside force to move. That's Newton's first law. Okay. So do you do you recall Newton's second law?
No. It has to do with force.
Does. It's basically the definition of force. So just force equals
Force
mass times
equals.
acceleration. Pretty simple. So his first law is saying that nothing happens unless we put a force into it, and nothing stops unless we
Mhm.
apply a force to it. And I'm so sorry. I'm absolutely allergic this morning. I took up some medicine, but oh, I'm having it. Oh.
Okay, I already had my mom.
And then we have one more of Newton's laws.
The third one
Newton's third law.
is the hardest one.
What makes it the hardest one?
I think it's because it's I think the video was talking about something about let's explain like it's always something about a force always acting on a force.
Pretty close, yeah. So it's the action reaction. So for every action, there's an equal and opposite reaction. Remember, energy, according to the laws of thermodynamics, right? Energy can't be created and it can't be destroyed. It
Mhm.
has to be transferred if in a closed system. So with Newton's third law, this is the idea of like a Newton's cradle. Um, are you familiar with those like little doodads that some people have in their offices with the like the five balls on a string, and they like pick one up and it hits the one and it goes like this.
Yeah,
That
yeah,
is exemplifying Newton's third law. When one the if a force is applied to like object A, and that object A comes in contact with object B will react with an equal and opposite force. This is why when people get into car accidents, that's pretty extravagant. It's pretty big, it's pretty messy. Um, but if somebody like falls on a bicycle, it's not nearly as bad because a lot of it has to do with the force involved with bicycle crashes versus car crashes. Does that make sense?
hmm.
Okay, so can you describe to me what is Newton's first law?
Newton's force law is an action and motion will stay in motion unless an outside force, um, or one put into like a vacuum, and then action, an object at rest stays at rest unless there's an outside force.
Excellent. What is Newton's second law?
The definition of force equals mass times acceleration.
Exactly. And then can you tell me Newton's third law?
Third law is like every action has an opposite or equal reaction. So we talk about the ball.
What about the ball?
Like when we hit one side, the other side moves because like energy is always like transferred or something like that.
Yeah.
It's
Yeah,
air.
exactly. Exactly. So Newton's third law is absolutely going to pop up on your test. It is super um
Yield.
it is a super high yield concept. So with let me think here real quick. Okay, I'm gonna do a practice question for you. Okay, we have, hmm, I actually don't know how to do this. Do you know what these little carrots mean?
What? Oh, raised to the.
Yeah, perfect. Okay. I just wanted to double check because I don't know actually how to.
Oh, what do you mean carrots? The colors?
The little arrow. Okay. All right. All right. Can you read this okay?
Mhm.
All right. I want you to talk me through this problem.
Okay, so we got a mass, just kilogram. I got math. Is passing through a space when it encounters a magnetic field. So now we're talking about a magnetic field that has like a number of Teslas. That could be the vacuum we talked about. Don't know yet. This exerts a force on of 2.5, a number on the particle that we put in a magnetic field. So now we got force. And then we got what do we have again? Then we have what is the acceleration of the particle due to the magnetical field. So of course we got F equals ma, and we got the mass, but we're trying to find the acceleration. But the thing is that we we trying to figure out, do we ignore the magnetic field and just deal with the force and mass, or do we use the vacuum it's in on how much it's moving? That's where I'm at.
Okay. So what's the question asking to solve?
What is the acceleration due to the magnetic field? So
So acceleration, right?
yes,
What is a formula that you know that uses acceleration?
force.
Force. So F equals ma, right?
Mm-hmm.
Do we have an F?
Yeah,
Do we have an M?
yeah.
Then we could go, right?
Mm-hmm.
So what would your answer be for acceleration? How are you setting it up?
2.5 over 1, and then my units of -12, no, -10. Take away -12, which is plus. And so now I'm looking at a 2. So 2.5 times 10 to the 2.
Well done.
So I was right. I do
Yep.
ignore it. Okay. Like, do I ignore the magnetic field? Okay.
So on the MCAT, they will have all kinds of information in the passage like this. But not all of it is necessary. So what I like to do is I like to go to the question and say, okay, well, what are we looking for? In this case, we're looking for acceleration. Okay, so acceleration is just force times or is force divided by mass. So do I have a force and do I have a mass? Yes, on both. Sweet, I can calculate my acceleration.
Okay.
The tricky part is that they put in more information, so you're like, oh, do I need to use that other information? But you do not always need to use the information that is presented. Sorry, you do not always need to use all of the information presented. Okay, now I have a question for you. If I have if I fire a ball from a spring on a table, a flat table, after the ball is no longer in contact with the spring, what's going to happen to the acceleration of the ball if we ignore air resistance? Sorry, if we ignore friction.
What happens to the spring? Like it comes back,
What
is what you're
happens
trying
to
to say.
what happens to the ball? Once the loaded spring fires the ball and the ball is no longer in contact with the spring,
Hmm. What happens to
what
the ball or
what's
the
going
spring?
to happen to the acceleration of the ball if we ignore friction?
If we ignore friction, acceleration remains constant
Exactly. Now, can you explain why?
because of Newton's first law that an action object in motion is always in motion.
Excellent. That's exactly right.
Okay.
Look at you. Slap out. You should now go to your resume, slap after your name physicist, because that's literally it. That is Newtonian physics.
Okay.
Okay. Now, if we didn't ignore friction, obviously the table will slow it down because the contact with the table will eventually create enough counterforce that it slows. But yeah, if we ignore friction, that follows the Newton's first law exactly. Well done. Okay. Once again, can you tell me what Newton's third law is?
And, and every reaction has an equal and opposite reaction.
Okay, can you explain what that means?
It means like no energy is like lost, it's just like transferred or like force. Is that not enough?
Well, the energy transfer is more of a thermodynamics.
Uh-huh.
Can you give me
So
an example of when of Newton's third law?
objects like the action of the object is like is transferred, not like Jesus the ball situation. Like you move one ball and it's just transferred to another ball because it's not like toys. It's transferred.
Okay, I like that. I'm going to use an example here.
Okay.
Man, I do not like being allergic. All right, we have a big old semi truck. All right, our semi truck is driving down the road at 100 kilometers per hour. It strikes a mosquito.
Hmm.
The mosquito is flying at like 0.5 kilometers per hour, and that's ridiculous, but just for the sake of it. What's going to happen to the mosquito? What's going to happen to the truck?
They're going to hit each other.
True. And when they hit each other, what happens to the mosquito?
Mosquito's not bouncing off. Dying.
So you're saying that the mosquito is going to
Splat. Yeah. Into
splat and then the truck is going to continue going, right?
yes.
What's going to happen to the truck?
Nothing.
Nothing? Like literally nothing or almost nothing?
It's not being pushed back.
What do you mean? Newton's third law states for every action, there's an equal and opposite reaction. Are you
Okay.
saying Newton's a liar?
Yeah.
Okay,
Uh,
so let's look at this conceptually, or sorry, mathematically. So we have a force of this truck, right?
mhm,
Ft equals mass of the truck
mhm.
times acceleration of the truck. And then we have the force of the mosquito, right? It equals the mass of the mosquito times the acceleration of the mosquito. Is the When the mosquito strikes the truck, according to Newton's third law, the truck will actually slow down a little bit because a force has struck it.
Mhm.
Now, is the change in acceleration going to be very big? Sorry, is the change in velocity going to be very big?
No.
No, it's going to be almost zero. In fact, it's going to go from 100 kilometers an hour to 99.999999999 kilometers per hour, right? Almost nothing has changed, but something has. So the acceleration here is going to be like a little itty bitty tiny acceleration of the truck. Now, is the mass of the truck large or small?
Large.
It's enormous comparatively. So we have like a massive mass and a tiny acceleration. But we know that the forces have to be equal. The force of the truck on the mosquito is equal to the force of the mosquito on the truck. This doesn't mean that the acceleration of the two is going to be the same. Is the mass of the mosquito compared to the truck large or small?
Very small.
Very small. Is the acceleration experienced by the mosquito large or small?
Small.
That's where the question comes in. So remember that acceleration can be positive or negative, right? If I have a rapid slowdown, like skydiving and striking the ground, that makes me go from a high velocity to zero very abruptly. That is a very high acceleration. It's just a negative acceleration.
Like as the force is moving down, it increases in like speed or something like that.
Yeah, yeah, yeah. Force of gravity causes you to increase in your velocity, so you're positively accelerating as you go down until you hit the ground. Then you go from whatever terminal speed you had to zero in an instant. And that is a very rapid deceleration. That's what causes death. So in this case, the mosquito went from going 0.5 kilometers per hour to the left and is suddenly now going negative 99.9999999 kilometers per hour. It changed its acceleration by almost 100, by almost 200%. Okay. That is a very large
When the
acceleration.
forces are equal. Oh,
So in this case, the acceleration of the mosquito
it's large.
is very large. So the force of the truck on the mosquito is equal to the force of the mosquito on the truck. The truck doesn't really feel anything because the mosquito is tiny. But if this were like baseball, a baseball has a little bit more mass. So the truck is going to experience a little bit more of a deceleration.
Yeah, that's the what the equivalence of like the window cracking.
Exactly. Now, if the truck slams into another car, a car is even more massive, so both of them are going to experience quite a bit more damage because the truck is slapping into something that has, even though it's less acceleration, it's going to have more mass. So that's going to change the acceleration of the truck. Changes in velocity or acceleration is what causes damage to objects. It's what causes death in people. It's what causes all these different things when people experience blunt force trauma.
Okay.
Yeah. So this is a good example of Newton's third law in action right here. For every action, there's an equal and opposite reaction. Okay. Outside of Newton's laws, what else did you cover in your study?
Look at my notes.
Yeah, absolutely.
Um, Scalar vs vector and
Okay.
kinetic.
What's the difference between a scalar and a vector?
They're both magnitude, but vector is direction.
Nice. Exactly, yeah.
Okay, that's what
So what's an example of a vector and what's an example of a scalar?
I'm asking for a lot. Uh, I don't know about the scalar, but would the vector be like something like Pythagorean theorem?
Hmm. So vectors and scalars are describing like variables or units. So I'll give you an example of each, and then I want you to come up with another example of each. So an example of a scalar would be distance. Can I have a negative distance? Like, can I say, oh yeah, this my car is negative 5 feet away from me?
No.
No. Distance can't be negative. Distance is a scalar. It only describes magnitude. Now on the other side, um, uh, distance with direction is called velocity. So if I say something is moving at negative 5 meters per second, that means it's going um, like behind and to the left of me if I'm looking north. So velocity means that we are moving in a direction, but that direction is changing with time. Velocity can be negative.
So you're saying that's vector.
Yes.
And then scalar is it's about just the distance that's being gone and magnitude is not it's not ever negative.
Correct.
Okay, so an example would be scalar would be probably like a question regarding like oh, I don't know, like inclined plane, like pushing a box at an angle and measuring
So
that.
that's going to use vectors and scalars.
Okay, so
But
then, oh,
think about it this way, distance is a scalar.
mhm.
Scalars and vectors aren't like problems or situations. They're describing the variables themselves. So,
The
so
difference I put in my notes is the difference between displacement and distance.
okay, I like that.
Okay, so like
Distance and
that
displacement.
that vectors deals with displacement, but scalars deal with distance, is what you're saying?
Yeah. So if I say distance, it can be in any direction and any number, right? But you can't have a negative distance, but you can have a negative displacement. Like if I'm running a race, here's the start, here's the finish. If
Mhm.
I run the race and I blah, 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 and then I stop and I have to go back and pick something up and then I keep going forward,
That's the displacement.
yeah. So the displacement would take into account going forward, coming negative, and then going forward again. My distance is the entirety of this combined. It would be like
This plus you doing that,
this
that.
plus that plus that plus that. So distance and displacement are a good example of a scalar and a vector. Nice. What else did you go over that we can discuss?
Kinematics. I'm sick of that. Do I really gotta memorize that? I don't remember that being next year.
Unfortunately, the MCAT will need you to know kinematics. I have not looked at kinematics since the MCAT, which means that in med school you're not going to need it, but you will need it for this test.
Yeah, I remember my exam. They didn't need no kinematics.
Yeah, it's kind of a hit or miss.
Okay,
Um,
so my thing with that is I need to figure out a way to memorize it where that I study it now, I still know it in January because when I studied it last year in January, I knew it for January and a few months after that. But when I took it in August, it was hard to like, oh goodness. What were the what was it, five? What was the five little equations that I had to memorize?
Mm-hmm. Like the manipulating equations.
Mm-hmm.
When you're talking about that, you're talking like V equals square root of 2GH.
Mm-mm. I'm talking about
X equals 1/2 AT squared.
mm-hmm.
And then there's T of your air equals 2V over G. This is for if you throw a ball in the air and it comes back down like a parabola. So with kinematics, the idea here is there are a couple of equations that you do need to know. That's true. Um, for example, and then there's that one equation. I don't really use this a lot, so I don't really remember it.
Yeah,
But
yours was
there is this one that's like V final equals,
the initial.
yeah, V naught plus like 1/2 AT squared or something like that. Plus,
Mm-hmm.
yeah, see, I don't remember. I don't remember because I don't really use it on the MCAT. These are the only ones that I use on the MCAT.
Those are the only ones that I need to know.
If you do know these, yeah, you're gonna be set.
Okay, so I don't need to know the other stuff.
I mean, you can know the other stuff, but if you know the other stuff, you don't need these.
Okay. I like
I
those
just I
three and
just like these because these are much more simple.
yeah.
So here's the idea. X here is going to just be like, why is it distance.
Uh-huh.
So my distance traveled is 1/2 of my acceleration times the time it travels squared. Pretty straightforward. Now, so well, okay, let's look at it this way. What are the units for acceleration?
It's the same as something else. Like I feel like acceleration has like the same usage as something else, and I put that there down
It's
somewhere.
very similar to velocity.
Yes. Oh, you talking about like meters per second squared or?
Bingo. Yeah.
Oh, okay, yeah. Okay, I thought you was talking about something else.
Okay. So acceleration is just a change in velocity. So it's velocity over time. So what are the units for velocity?
Meters per second.
Bingo. Yeah. So it's just meters per second divided by second or meters per second squared. What are the units for time?
Seconds.
Bingo. So if we have time squared, we have seconds squared. Cancel, cancel. We're left with just meters. Meters is the unit for distance. So this formula right here makes pretty good sense. X being distance.
What do we do with velocity?
What do you mean?
So with one of the kinematic equations that deals with distance and the half AT, it has initial velocity.
Mhm.
What do we do when we have a question that comes asking us for distance, but it provides us with velocity? Okay. So
That
what?
H is a distance. That H is height.
Hold on, I'm trying to debunk your three equations.
That's okay.
So then what do I do when I have a final and initial velocity?
Take the
Like,
average.
which is subtract them or take the average. Like
Yeah,
basically do
you can use
VF minus VI.
um no. So final velocity. So yeah.
VS minus V initial.
Yeah, but that's just the change in your velocity.
That's only when
Um,
it has changes in velocity. It's usually
you take the average, so you take the starting velocity, add the ending velocity, divide by two.
oh like no average them like actually average them.
Uh-huh. And then that's your average velocity, and then you're fine. Does that make sense? So if I have like a starting velocity of 0 and an ending velocity of 100,
Mhm,
while I'm falling down, at about at whatever point, the average velocity here is 50, right?
mhm,
So if we're looking at like how much distance did was traveled,
mhm.
at 0, the distance is 0. At 100, let's say the distance is, we'll say that they're falling at 10, so 100 velocity, 100 meters per second, 10 seconds. We've gone 1,000 meters. Okay. Okay, so if we've gone 1,000 meters by 100 seconds, the idea here is that at, 10 meters per second going down, we've probably gone 100 meters. By 50 meters per second, we've probably gone 500 meters, and so on and so forth. The average velocity is just taking the start and the end, and it's just saying somewhere throughout this line, we're averaging out this much. So taking the average velocity and slapping that over here is totally fine.
Okay. What if they give you your like your V initial, which is 0, and they ask you for your V final?
Yeah, in that case, um, they're looking for the final velocity. They'd have to give you distance traveled, in which case, yeah, you could just look at this as V final plus V initial divided by 2 equals square root of 2ax. And if they're asking you for your final velocity, first off, I don't really think that they do that. Yeah, I don't know if they actually do. Oh, no, here we go. Here we don't. Yeah, no, I don't usually see a question about that on for the MCAT. But if they did ask something like that, you could just calculate it via um distance traveled, acceleration about the travel, take the initial velocity, multiply this by 2, and then subtract the initial velocity from it, and that should give you the final velocity. I wouldn't worry about final velocity calculation very much for the sake of this test. Mostly when they bring up velocities, they're going to be applying it to a force or trying to calculate a distance.
Perfect. I can remember those three things. Give me a moment.
Oh, just so you know, the last thing here, T air. This is the time in the air. So if I fire a ball up in the air,
Mhm.
I'm going to take into account the velocity and the gravity. So if I fire it at 10 meters per second, it's going to be going up at 10 meters per second, obviously. Gravity is going to be pulling it down at 10 meters per second squared. So then it's going to be just 20 divided by 10. The time in the air is 2 seconds.
Huh?
If I fire a ball straight up in the air at 10 meters per second,
Huh? And now you got the meters. All you got to do is get the seconds.
well, I have the meters and the seconds right here. And I want to eliminate the meters
Hmm.
and I want to put seconds. So what could do here is I could just multiply 10 times 2 here, according to this equation, divided by gravity. And then that's 10 meters per second divided by 10 meters per second squared.
All right.
Time in the air, 2v over g. All right. So with kinematics and everything, there are some questions that can pop up relating to like a ramp or linear motion. Um, have you gone over those? Have you reviewed them? Have you practiced that?
Okay, so I did on the video we went over one with kicking a ball and that like hyperbole thingy.
Hmm.
So we did that one with like, our sine cosine situation, but we were also measuring like the ball vertically, like that one. And then we did another one where we just did a regular one where I don't remember the what's it called it, but we just solved like a regular kinematic equation searching for distance. But we had V initial, we didn't have V final acceleration and time. Excuse me. So basically the equation you have, and we just measured
Okay.
for distance. Yeah.
All right. So I think the next time we meet, we could go over those.
Okay.
I just because I have to log off today for right now.
Okay, that's fine. Oh, we did an hour studying.
Yeah, you're doing great, honestly. Like I feel like your confidence is shot, but you know your stuff. You know what you're talking about. You get in, you can calculate fairly well. I was impressed with how quickly you were able to calculate up here the acceleration.
Yeah,
Um
because I've been working on MCAT math.
yeah.
Ridiculous,
So
like, but yeah, I've been trying.
but I think you did really well. I'm gonna stop sharing here and
Just keep doing my like notes with the other ones. I feel like I'm behind because I didn't finish working energy on Tuesday and I didn't do Wednesday. Wednesday.
okay.